Hello, everybody. My name is Hope Redhead, and today I'll be discussing the topic of shear flow dispersion and its relevance to the distribution and mixing of pollutants in fluid environments. The goal of this presentation is to explain the mechanism of shear flow dispersion and its impact on pollutant distribution in various fluid environments such as rivers, lakes, oceans, and the atmosphere. But first, we have to go over some key concepts, starting with advection. Advection is the transport of a substance or quantity by the bulk motion of a fluid. For example, pollutants carried downstream in a river by the flow of water are transported through advection. Next, we're going to talk about diffusion. Diffusion is the movement of molecules from regions of higher concentration to regions of lower concentrations due to random motions. An example of diffusion is the spread of dye on still water, like we saw on the first day of class. Next, we're going to talk about shear flow dispersion mechanisms, starting with velocity profile in shear flow. So in shear flow, the velocity of the fluid varies across the transverse directions, such as the depth in a river. This means that fluid parcels at different transverse positions travel at different speeds. For instance, in a river, the current is typically faster at the surface and slower near the bottom due to bottom friction. As you can see here, we have quite a smooth surface and quite a rocky surface, and you can see the differences in velocity profiles. Next, we'll talk about the differential advection. So different layers of fluids move at different speeds, causing faster moving layers to overtake slower ones. This leads to a stretching and folding of the pollutant cloud, intensifying concentration gradients and promoting mixing. A good example of this is when a cold front comes in and is moving at a different speed or direction compared to the warmer air below. This can then create complex weather systems and is super interesting. Next, we're going to talk about enhanced diffusion. So the differential advection brings fluid parcels with different concentrations into close proximity, hence enhancing diffusion. This process helps spread the pollutant from regions of high concentrations to regions of lower concentration. And in this image here, you can see trajectories of absorbates. So this image shows a path taken by particles or absorbates on surfaces that are oscillating. This oscillation can enhance the diffusion of the particles compared to static surfaces, which are pretty cool. And lastly, we're going to talk about transverse diffusion. For shear dispersion to occur, there must be diffusion in the direction transverse to the flow. This transverse diffusion helps to smear out the concentration differences created by differential advection, leading to a more uniform distribution of the pollutant across the flow, which you can see quite clearly in this image here. Moving on to the mathematical description. So the concentration distribution of a pollutant in a shear flow can be described as the advection diffusion equation, which is right here, where C is the concentration of the pollutant, T is time, U of Z is the velocity profile in the transverse direction, Z, X is the streamwise direction, and D is the molecular diffusion coefficient in the transverse direction. All right. Lastly, we're going to talk about the implications for the pollutants, starting with longitudinal spreading. So the combined effect of the differential advection and transverse diffusion results in the longitudinal spreading of the pollutant. This means that the pollutant spreads more rapidly along the direction of the flow than it would by molecular diffusion alone. Effective diffusivity. So the effective diffusivity K in the longitudinal direction is influenced by the shear flow and can be much larger than the molecular diffusivity D. This effective diffusivity is inversely proportional to D, meaning that stronger transverse diffusion can reduce the longitudinal spreading by homogenizing the pollutant concentration more quickly. So then moving on to the environmental impact. In natural water bodies and the atmosphere, shear flow dispersion plays a crucial role in the transport and dilution of pollutants. For instance, in rivers, the current is typically weaker at greater depths due to bottom friction, creating a shear flow that enhances the dispersion of contaminants introduced at the surface or from a point source. In summary, we have discussed the basic concepts of advection and diffusion, the mechanisms of shear flow dispersion, and its implications for pollutant distribution. Understanding these mechanisms is crucial for predicting and managing the spread of contaminants in natural water bodies and the atmosphere. Thank you so much for listening to my presentation. Does anyone have any questions?